This video series is about conducting multiple linear regression with mixed variable types. When I began this course, we started by looking at multiple linear regression with quantitative explanatory variables. In all of the examples that we used, we always had a quantitative response variable, and that will continue to be the case in this video series. Once we were done looking at multiple linear regression with quantitative explanatory variables, we switched to categorical explanatory variables. Many people call that analysis of variance, but as you have seen, we actually use analysis of variance regardless of whether the explanatory variables are categorical or they're quantitative. Now it's time for us to take the next step, and that is to mix the two. Have both categorical and quantitative explanatory variables. And again, we will have a quantitative response variable. Let's start by learning a little bit more about using categorical variables in regression. How does that work? How do we use multiple linear regression with categorical variables? The way it works is that each of our categorical variables must be converted to a series of binary variables. Statistical software codes are referred to as dummy codes. So we create dummy codes for a categorical variable to indicate each of the various levels of a categorical variable. Let me give you an example of this. Let's look at the plain risk analysis example that I showed you when we were learning how to use a single categorical variable in a multiple linear regression, so-called one-factor analysis of variance. So let me go ahead and knit this, and so that we can have a cleaner looking output here. Here we go. And I've left in all the codes so that we can remind ourselves, with the exception of I did not leave in the reading in the data, so let's go back and look at that. So reading in the data here, we read in the plain risk data, but here's the key part. When we did so, we indicated that the view variable in the plain risk data was going to be a factor. That is, we are going to have 3 different levels of that categorical variable, and we're going to label them as individualist, hierarchicalist, and egalitarian. So just to jog your memory, assuming you've watched the past videos, the individualist is a particular worldview, as are the hierarchicalist and egalitarian. They're worldviews. And what we're looking at here is the perception of risk of riding on an airplane to see if it seems to be related to worldview. Here is the box plot. I'm going to switch back now to the output. Here is the box plot in which we found that there was less of a perception of risk for egalitarians than there was for hierarchicalist and individualist. And we also saw these over here in the means, where the means were similar for individualist and hierarchicalist, but lower for the individualist. So that is the descriptive statistics, the description here, and the graphical display that we used when we were learning how to deal with a single categorical explanatory variable. But now I want to show you what's going on behind the scenes when we use this particular factor function, this factor function in R, in which we're telling R that plain risk view is a categorical variable, not a quantitative variable. So what you'll see here is that I've gone ahead and added some dummy codes. And dummy codes simply are binary variables that indicate what level you have in your data. And so I'm going to indicate a dummy variable for hierarchicalist and a dummy variable for egalitarian. Now notice up here that those are the second and third levels of the category. I don't need anything for the first level. Well, why is that? Because if I indicate that someone's in hierarchicalist or they're in egalitarian, if they are not in either of those, they must be in individualist. So we only need one fewer dummy codes than we have levels of the categorical variable. This individualist is referred to as our baseline for reasons that we'll see here in just a moment. But let me go ahead and show you in the environment what the variables look like. In order to do that, I'm going to have to do a run all here. So let me go ahead and run all. All right. Now I can go back to our knitted values, and let me get rid of that. For some reason I'm having that, okay. Having that, there we go. Having that blue over that screen. All right, so now we're back here, and remember I added these dummy codes to plain risk, and I called them D1 and D2. So let me go ahead and look at our plain risk data. So here's our response variable, the score, and here is the view after we converted it to a factor. So we have converted this view already to a factor. So what's happening behind the scenes that I'm now actually putting in front of us, because I did this by hand to show you what's happening behind the scenes, is that these dummy variables are being created. So hierarchicalist has a value of 1 on dummy variable 1 and a value of 0 on dummy variable 2. Egalitarian has a 0 on dummy variable 1 and a 1 on dummy variable 2. And if I go down and find on line 9 my first individualist, there is 0 on both. That is, because they're not in either the hierarchicalist dummy variable or the egalitarian dummy variable, then they must be in another category, and that's the individualist category. So there are 2 dummy variables needed in order to create 3 levels of a single factor. All right, so now what can I do with those? I don't actually ever need to create those because it's happening behind the scenes. I'm just bringing it to the forefront now to show you a couple things about how this works in multiple linear regression. So the first thing I'm going to do is create a model. I'm going to call it model 1, and I'm going to create this linear model with the LM function, create this linear model and get a summary. And you see what we get when we get a summary is this particular model is showing us each of the individual effects for hierarchicalist and egalitarian. So if you have 2 dummy variables, you're going to have 2 effects, and there they are. Now that's in addition to the intercept. Well, the intercept right here does have a meaning. That 38.96, let's go back up to our means. That intercept is actually the mean for our baseline group, individualist. Intercept in all of multiple linear regression can be seen as setting the baseline, and here we're setting the baseline as the mean of the individualist. So that's the value of the intercept. So individualist actually is in here, even though we only created 2 dummy variables, and even though we're not seeing the term individualist here, we're seeing intercept. When we look at hierarchicalist, there's a negative 2.037. What is that? That's the effect of hierarchicalist. Remember, whenever you do multiple linear regression and you're looking at those coefficients, they're telling you the effect size. When we did it with quantitative variables, it was the slope. Well, here with categorical variables, that's also an effect size, and it's an effect compared to our baseline. All effects are compared to baselines, and so the effect here of negative 2.037 is telling us, if we look back up here, that hierarchicalist is 2.037 below individualist. Similarly, for egalitarian, we're seeing that it is 14 below individualist. And here's that 24.92, which is the 14 below the 38.96, the 14.038 to be more specific below. So we're actually seeing the effects, and there are two of them, hierarchicalist compared to individualist and egalitarian compared to individualist. Now you might wonder, what about egalitarian compared to hierarchicalist? That's not a unique effect. If we know those first two, we could mathematically figure out the difference between egalitarian and hierarchicalist here. Now I did this using the view variable, which remember we had created as a factor. We made view a factor. If I look over here under plain risk, I can see view as a factor with 3 levels. Okay? Let me do this again, but instead of using view as a factor, let me put in a linear model where we're not using a particular factor, but rather the dummy variables that we're created. And those dummy variables, R thinks they're numeric. But because they only have 2 levels, they're really the same as being factors, because you can't have numerical order with only 2 levels. You need at least 3 in order to have a numerical order. So even though R views these as numeric, we know that there are only 2 values possible, and therefore they're just like having factors. And so look what happens when R considers these as numeric, but they're actually binary variables, and we run this. Look at this. We get the exact same thing that we got up here. Now, instead of the labels of hierarchicalist and egalitarian, we're getting the labels of D1 and D2. But this is the same as up here. So all I'm showing you is that when you create a factor, here's what's going on behind the scenes, is you are having dummy variables created, and the number of dummy variables that are being created is 1 less the number of levels. Now let's do some analysis of variance by looking at sums of squares. And I'm going to start here with that second model that I just created to get the sums of squares. When I get the sums of squares for the second model, because R thinks that D1 and D2 are separate numerical variables, it's giving us the sums of squares for each of those numerical variables. But you know that when we do analysis of variance with categorical variables, you just usually get a single sum of squares for the effect of that categorical variable. Let me run ANOVA again, this time with the first way that I coded it, up here in Model 1, where we indicated that view is a factor. And sure enough, you only get a single sum of squares for the effect, plus 1 for residual. Well, compare the two ANOVA tables, and what do we have? We actually see that those first 2 variables here, D1 and D2, the sums of squares combined make the sums of squares for view down here. And that's what's going on again behind the scenes when you have a categorical variable, that R is creating these dummy variables, but furthermore, it knows that you want to know the total effect, and so it combines the sum of squares for each of the individual effects and puts them here in this total effect. Note the residual is the same. So these two ANOVA tables are basically the same, except for up here in the first one, it's been partitioned into 2 effects, and those effects, by the way, are sequential. So the second sum of squares is above and beyond the first sum of squares, but we don't worry about that if we're actually going to combine them, which is what we do when we do categorical analysis of variance. So this is just showing you what I stated in this particular slide here, is that for categorical variables in regression, you convert to a series of binary variables, and the statistical software codes are referred to as dummy codes or dummy variables. Now, there are various coding schemes. In the coding scheme that I just used, I used the scheme as we saw over here of 1 for hierarchical list and 0 for when it wasn't hierarchical list, 1 for egalitarian and 0 when it wasn't. What that coding scheme did is it gave me the particular effects that we saw up here in, let's see, where was it? This table right here. It gave me those effects of looking at the difference from baseline to each of the hierarchical list and egalitarian. But there are different coding schemes that would give you different kinds of effects. So if you were interested in this in a different effect format, you could use a different coding scheme. But what would not change is the sums of squares will still be the same for that categorical variable. If this was my experimental design class, we would spend more time looking at different coding schemes. But here we're just going to stick with this one simple and fairly common coding scheme of comparing the means for each of the levels of the categorical variable, each of the levels of the categorical variable to the baseline in that particular categorical variable. Analysis of variance models are just regression models with one or more categorical variables and a quantitative response variable. So I don't like the term analysis of variance in that particular, for only that particular case when you have categorical explanatory variables, but I'm just reminding you here that's common nomenclature. That's what people say is that, oh, you're doing an analysis of variance, meaning that you have a categorical explanatory variable, but we have seen that we do analysis of variance regardless of whether it's categorical or quantitative explanatory variables. So it's just something to get used to. It's kind of stuck in our statistical language, but really all we're doing, as you just saw, is we're doing regular old linear regression, multiple linear regression with dummy variables. And so that is how we use categorical variables in regression. We'll expand beyond categorical variables in the next video.